Last week we were talking about transformation formula and properties of uh, index quantities, and vector transformation formula is derived. You need a transformation matrix to calculate components of a vector in different coordinate systems, and such a quantity then obeys the transformation rule, and it's then called a first order tensor or a vector. This method can be extended by considering higher order tensors, and we will need transformation formula for higher order tensors as well. And the first of these is a second order tensor. Let me show the file first. Thus, we'll be talking about transformation of higher order tensors, and we will see how this can be extended. And this is therefore transformation of higher order tensors. And you need two first order tensors to obtain this formula. Suppose that these first order tensors are u sub I and v sub k. These have three elements each. And I can apply vector transformation on them, assuming that they are vectors. According to our transformation formula, uj prime is aij ui. This aij is transformation matrix. And vl prime is akl vk. This was derived last time. And consider outer multiplication of this first order vectors. Let's multiply that, and you get uj prime times vl prime. This is equivalent to aij akl ui uk. And this is nothing but the tensor transformation or transformational formula for a second order tensor, because you can think of the left side as a second order tensor. This has two indices, j and l. There are two free indices. You can think of it, for example, as AJL. This is equivalent to, or BJL. This is equivalent to AIJ AKL times UIVK. Thus, this is BIK. And these are the elements of the tensor in the original coordinate system. And these are the elements of the tensor in the primed coordinate system. And we are denoting this outer product ui times vk by aik. And the other one then, of course, is jl prime. And the formula is actually in this form. AJL prime is aij akl aik. And the indices ijkl, there are four indices here. Each of them varies from 1 to 3. This is called second order transformation formula. It's again written one more time on this line. Same result. In this case, the tensor is w, wjl prime equals aij akl wik. Now there are four indices, ij, kl. J and L are free indices here. and I and k are dummy indices. Now, how many elements does this quantity possess? Wik, for example, how many elements does it have? Wik.
9.
9 elements, that's right. There's 9 elements, and there's Onat also gave the correct answer. So there's 9 elements, but for each element we have a summation over I and k. Sorry, j over j and l. No, the summation is over I and k, and j and l are free indices here. J and L are free indices on the left side, but as a separate term, Wik has 9 elements. Here it's a part of a summation. Thus, this has a total of 9 elements. Wjl prime has 9 elements. This is index notation of this transformation, and you can also write it in matrix form. The matrix form can be shown as shown here. That's the matrix form. Matrix form is W prime is a transpose W times A. W prime is the matrix, 3 by 3 matrix in the new coordinate system. That's equal to a transpose W times A. W is in the original coordinate system. And can you give examples for a second order tensor? Can you give examples on this? Any quantity transforming in this way is named as a second order tensor. And yes or not as the correct answer. Stress, for example, sigma j, transforms as a second order tensor. Its components can be calculated in a new coordinate system. And strain also transforms as a second order tensor. The examples are given here. We will talk about stress tensor, sigma ij. It has 9 elements, and it transforms according to this definition. Now you can proceed to construct higher order tensor transformations. This was a second order tensor. But if you multiply 3 vectors, you will get a third order tensor. The idea is the same. Now, 3 vectors are defined. Vector transformation formula for these 3 formulas for these 3 vectors are written. For example, UP prime is AIP UI. And VQ prime is AKQ VK. ZR prime is ALR, ZR. Each is a vector transformation formula. Multiply them and define this product UP prime, VQ prime, ZR prime is a new quantity WPQR prime. On the right side, define then UIVKZR is defined as WIKL. It's on the right side. Thus, transformation matrix appears 3 times here in the transformation formula pertaining to this third order tensor, WPQR prime equals AIP, AKQ, ANR, WKL. How many elements does this symbol have, WPQR prime? How many elements? There's an answer, I guess. No, attendance is taken. And how many elements? Yes, it's WPQR prime. It's 27 elements. That's right. For each element, you have to carry out a summation like this. Of course, you can write a short script and you can or include this in another computer program. This can be easily handled by writing such scripts. And fourth order tensor obviously involves four transformation matrices. Examples of third order tensors can be given. We have talked about alternating tensor, but this is isotropic. It is an isotropic tensor. What's an isotropic tensor? As I have mentioned it last time, it's not as defined this way as an initial quantity, but its components are the same in all coordinate systems. This third order tensor is not affected by coordinate transformation. There could be many other applications depending on the problem. Consider elasticity tensor is mentioned, EIJKL. This is also defined in elasticity. It has four indices, around 81 elements, and you can construct the transformation formula for EIJKL. It's used in generalized Hooke's law, actually, sigma j, EIJKL, epsilon KL. It's a general form for generalized Hooke's law. We will later simplify this. Now, I'm going to give you an example on this computation. An example on transformation formulas. The components of displacement and stress in a particular frame of reference are given. Certain units had to be given as well, but these are either dimensionless or they have certain appropriate units. This vector u is this displacement vector, it's two elements, and it's stress. Now I'm going to compute these components in a different coordinate system. That's the original coordinate system, and this new coordinate system is defined here. A new coordinate system found to a rotation of 60 degrees about the x3 axis. Choose a counterclockwise rotation when viewing down the negative x3 axis. These definitions are important. We may define such sorry about this. We may define such simple definitions. We were considering this example on transformation. These are the matrices. It's the new coordinate system. There's a 60-degree counterclockwise rotation about x3 axis when viewing down negative x3 axis. That's our original coordinate system, x1, x2, x3. It's the new coordinate system. And we have to construct a transformation matrix. And for example, so that's Aij or A. What is A11 for this matrix? What is A11? Yes, Emre gave the correct answer. It's cosine 60. It is the angle between x1 and x1 prime, 60 degrees. And it's therefore direction cosine is cosine 60 degrees. Then what's A12 for this transformation matrix? What should be A12? Any answers on this? Yes, Emre and Donat, cosine 150. And A13, what's A13 here? The other elements. That's right, cosine 90. 1 over 2 minus square root of 3 over 2 and 0. That's the first row. And the other elements are written in a similar way. There's the transformation matrix. And to facilitate this computation here, on this column, you write the original coordinates. On this row, you place the new coordinates. And then the angle between 1 and 1 prime, cosine 60. It's 1 over 2. And 1 and 2 prime, cosine 150. 1 and 3 prime is 0. 2 and 1 prime, this is cosine 30. 2 and 2 prime, cosine 60. It goes on like this, and transformation matrix is formed. Transformation matrix, it should be orthogonal matrix. Its transpose is equivalent to its inverse, or A times E transpose is transpose times A, and that's the identity matrix. That could be a check. Now introduce transformation formula to find components of the vectors in the new coordinate system. It's a straightforward computation. U prime, for example, is A transpose times U. A is known and U is given. Therefore, the result is by matrix multiplication. These are the elements of this vector in the new coordinate system. 3.96, 1.13, and 2. The third axis is not changed. And stresses in the new coordinate system can be found. Sigma prime is A transpose sigma times A. This multiplication gives stress in the new system. So these are the stresses in the new system. This was normal stress sigma 1. It was 1. Sigma 1 to shear was 0. And normal stress is 1.75 here, and shear stress 1.433. Stress depends on normals of a plane and directions associated with the coordinate axis. Well, we will see how stress is defined, but that is general stress transformation. I can extend these techniques. This is done by math packages or writing simple scripts. But in the exam or quiz, you may be asked to do this by hand or by a calculator. Any questions on this example? That was a simple example on the coordinate transformation, and as I mentioned, it can be extended for higher order tensors. In the next hour, we will be talking about some special tensors. One of them is gradient of a scalar function, which is a vector. The gradient of a vector is encountered in definition of string. We will define that as well. And integral theorem, certain identities are written in index notation, and we will give an example of that as well. So now we can have a break, and I will continue after that.